My talk is the most pedestrian, which means it's going to be hopefully a little bit fun, and I'm sensitive to the time, so I'm going to just try to fly through this. But you think about engineering economy, what's going on? Well, Brian's work was pretty diverse, and one of the things that he benchmarked was by doing things to membranes, could he increase the flux, the liters per meter squared per hour, the throughput of whatever he's looking at, the BSA solutions. Because if he could, that meant he can use less material, make smaller devices. And everything he developed commercially, including at Hemocell and other places later on, Brian was always interested in as we all know, in benchmarking, figuring out where are we now and what were we at before we had now. And that's the beginning of engineering economy. And so my talk today is going to basically touch three things. Basically, Brian's straightforward approach, three examples from more modern times, how I've grown with that approach in the application of engineering economics, and some continuing work. And just so you know, I come from the brewing world. And so I'm a brewer. I was a brewer long before I ever came to the MEU, and I was a brewer immediately afterwards. After I left Oxford, I finished building and commissioning a state-of-the-art brewery in Rajasthan, India. But Brian always liked having a brewer around, and I do appreciate that. And I guess my talk's gonna be a little bit more, I say, pedestrian, because brewing is not rocket science. I mean, let's face it. It's the second oldest profession. And for the young people here, just ask your father what the oldest profession in the world is. But so it's not rocket science. But just to show you, the companies I've worked for after I left the Oxford, I went immediately to Stroh Brewing Company. And then for 15 years, I was the director of brewing operations for an interesting family-owned company with multiple breweries. So we had some of the beers. If you go to the States, you'll see some things like Shiner Bock. It's world famous in Texas. And we had Oregon. We had a little brewery in Salzburg and another one in Berkeley that I built. Pete's Wicked Ale, which we brewed at the New York Brewery. And then I built a brewery with some partners that's doing well in Pennsylvania, Susquehanna Brewing Company. And most recently, I was at a Beta Brewing Company just right outside New Orleans in St. Tammany Parish, above Lake Pontchartrain. So let's go into this. Well, let me just reprise something that Ian shared. Brian's first paper that actually showed pictures of a unique device comes back from 1973. The wonderful thing is you can still look it up. It's a PDF file. You get the same, the whole article. But most importantly was these devices which were made by the technicians, the very adroit and adept technicians within the medical engineering unit. And Brian's interest in working with first the dimpled devices. You saw a picture of the dimpled devices, for example, was by using pulsatile flow, which was superimposed in steady flow, he got higher fluxes. The rate of concentration polarization, the fouling, was lessened. And then Brian next moved on in conjunction with people he was advising or collaborating with using flat membranes that didn't need any work done to them to make those dimples, but they used as you saw from the patent that Ian shared, the picture, they used those little walls. And that was Brian's first real example of exploring the engineering economy space. By using that approach, he saved the machining mechanism of making these little dimples. He can get an off-the-shelf sheet and use it. But he was actually blinding, occluding part of the surface. So he had to determine, okay, I've just lost 8% of my surface area because it's being blocked. I don't have a workable surface. Is the amount of the efficiency, my throughput, going to be increased? Is it going to be greater? Is it going to be lesser? So those are the kinds of questions that Brian worked with. And those of us who followed, we were all allowed to come up with our own ways of exploring that space. I think of Brian Moore at the MEU as kind of like an artist. And there was his canvas, and all of us were doing a little bit of painting. until we finished a full picture. And you'll see some of the people who couldn't be here did some interesting things. But Brian and I only have one paper. Can everybody hear me okay? Because I'm kind of walking around. Brian and I only had one paper. And even the way the paper, you know, the prestigious journal was the Journal of Membrane Science. And I came to Brian after we did the work. And Brian really guided this work. I said, Brian, I know it's important to get this peer-reviewed, and the Journal of Membrane Science is the gold standard. But if I go into the secondary journal, also from Elsevier, but you know, a much lower grade journal, they've invited me to present my work in Karlsruhe, full pay, a conference. And Brian knew me as his brewer, that I kind of needed some crutches. I needed some help to get through. Ian was on my first Viva, which was when you go from a provisional student, a provisional PhD to a PhD candidate. And I reminded Ian today that he was very interesting because he asked me 3 questions during the thing. One was an easy question. I know he knew I could answer. One was a more complex question, which was to try to explain the difference between a standing vortex and the vortex wave. And the third question he asked was one auspiciously to see, it was more of a rhetorical question, but I think Ian was just reminding me that I was a student still. I shouldn't get too cocky. But Brian knew the only way I was going to get through my DPhil, which I did, I've had a great career, but to get through was probably to have a series of peer-reviewed papers that I published, and then I read together. I thread together my dissertation after those, and those would be the appendices. But my work with Brian, again, you see the vortex mixing. My little thing was I used electrofiltration. Oh, you can't see it. We've worn out the batteries. I invoked electrical fields. So I had another thing going on. We had the vortex motion, in which they flow through this channel, going back and forth in oscillatory flows. And then my work was imposing electrical fields. For example, I had a ladder. It's hard to see this like this, and this came from the paper, but these separators would be sitting basically on top of 2 parallel membranes. And all I did was I made those positively charged, and on supporting the membranes, I had stainless steel, porous stainless steel. I made that negatively charged. We were separating things that were highly negatively charged. So by imposing an electric field, not only did I have the vortex wave helping scrub them, but I had an electrokinetic thing. And later on research, after I published this one, was I created a sweeping field. We changed that a little bit, so we had little tabs on all these, and we did a transient sweeping field, electric field. So Brian's interest in there was, okay, we've got something, and now we've added on, but the good part is we can have a smaller surface area to get the same flux, but there's a penalty. The penalty I've already talked about is losing the surface area contact here, but now I'm using electricity. And the electricity I'm using is to overcome. This is something that's got saline in it, so we're continuously exploring, consuming electricity. So we came up with stuff with a really good exploration. Did I just jump through some slides there? That's right. Yeah, I did. Okay. Let me go back over here if I can. Yeah. Okay. So after we got data, Brian said, because I came from industry, I came from the brewing industry, I was used to scaling up stuff from bench or pilot to big to larger scale. Brian said, go for it, Jaime. Let's come up with something that makes sense, that you can use the data you have and apply it to a theoretical design. And something that was available easily was whey. Typical whey concentration when you get it from dairy is 1% whey protein. And to make something like cow and gate, when they make their whey-based baby food, it's 25%. So we had some real parameters to say, let's use what we've learned on this, design to scale up. And if you see, the design this paper was on, oh, you really can't see it very well. But there was 4 things. We had 4 different kinds of situations. We're going to design and look at the size of the membrane needed, and also quantify the electrical consumption. So, basically you have whey coming in, 10,000 liters per day, 1%. In 3 stages, it would end up 25%, a semi-continuous concentration. And, I calculated, Brian said, you've got to calculate the power of pumping, and let's quantify the power of the amount of electricity used. So I found the equations and applied them to find out how much power. And eventually, mathematics was done, and we came up with a number of how much and what the surface areas were going to be for the various membranes. And again, the takeaway from that is the economy. Brian wasn't even talking about economy. We were trying to increase the flux, which naturally meant decrease the resources we're using. And the penalties were things like the surface area being included and also the energy that I consumed when I was adding. Later on, one of my good friends, Siamak, was doing his PhD, came a year after I did, and he took Brian's ideas of the vortex wave and came up with reverse pulsing. So he took some of the permeate, pushed it back. Siamak's now a professor at Cone Tech, right outside Tehran, and couldn't be here today. As he describes, the MIT of Iran. It's funny because if you travel around the world, inevitably, you never hear a place, oh, this is like the Oxford of Guatemala. It's always, this is the MIT of Guatemala. And some of these, I've been to a couple of these places, and you say, this is more like being the headmaster of a homeschool. But anyway, but no one ever talks about this is the Oxford of, because I guess Oxford's so unique. So now I'm going to show you some real world, quick 3 examples of the real world of engineering economy. But I have to say, Brian gave me that orientation. We all have it, We're doing something, we want to innovate, we want to show that we've done something that's better than we had before. So it's in our genetic code as engineers. But here's a situation, a typical situation, a practical situation. This is from my brewery in Louisiana. Now, why won't it advance? Why won't it advance? Sorry, this thing is acting up. Come on. Oh, I won't. All right. Okay, so I had a room, I had to cool it, I had to keep it insulated and cooled, and we have 2 simple options. You can use a rock wool, Baumwolle, as they would call it in Germany. I studied brewing in Germany. Or you can use foamed on insulation. So, simple thing that we have 2 different materials. They cost at different amounts, $25 per meter squared. They have different conductivity rates through them. So, we familiar calculations. We all knew this when we were, our first year of engineering, of how to calculate using the constraint that the world-class standard is. This cube is going to be 30,000 or less. So 30,000 is the world-class number. So basically, you have the heat transfer coefficient, you have the change in temperature. In this case, it's a 43-degree environs. It's pretty warm in Louisiana, in New Orleans. But I wanted the interior to be at 13 degrees. So it's like a 30-degree centigrade differential. So we just calculate the L. I mean, this is really easy stuff. This is engineering for brewers. And basically the cost, you can see that the rock wool, because you need a greater thickness, because it has, its conductivity is greater, it pulls the heat away, you need a greater thickness, the insulation is cheaper. That's just a simple example. Another simple example is putting a centrifuge to replace classic diatomaceous earth filtration. In that, when you do it, I percent more beer. So the brewery that I installed this in was basically, we knew that the yield would be increased from 2 to 5%. So in brewing terms, that meant that I'd get, at the end of the year for this particular brewery, I'd get 66 truckloads of extra beer that I could sell, or 27 truckloads at the low end. That gave us an idea. And when we installed it, this piece of machinery cost $410,000. And then it cost me another $80,000 to install. It's not very pretty because we actually did it ourselves. We mobilized people from other breweries, our sister breweries. We came in and we had a stainless steel welder. So It's not as pretty as it could be, but it runs very nicely and still. And its payback was pretty fast. The third example is membrane filtration, sterile filtration versus pasteurization. Most large breweries have pasteurizers. They cost a lot of money. And all that happens, your milk, your whatever you have, your beer comes through, and it gets heated up in stages, gets up to 140 degrees, where we have a log reduction of any viable organisms, and then we cool it down. So the option is sterile filtration. Now, you don't have to do this, but if you're a major brewer exporting around the world and you want 8 months of shelf life, you sleep better with some kind of treatment to make sure that nothing in that beer will never get you sick. But if you have microorganisms you don't like, Brettanomyces, Acetobacter, you'll never get sick, but you'll change the flavor from what the brewmaster wants. And we don't like our flavors changing. Of course, the secret to this brewmaster is, you ever get a complaint, you always blame the customer. No, it's very perfect. You go, Jesus, it's awesome. But you always keep your poker face on. But so this is the amount of energy used. Hockenceller in Germany was doing his research, quantifying it. Singleton was up at Heriot-Watt University for flash pasteurization. Membrane filters, this was somebody, Pacific Gas and Electric in the Pacific Northwest, all about the same time. And there's a process. I won't go through it. I love it. I give lectures in engineering economics, seminars. The last one I gave was at Georgia Tech. They invited me for an hour-and-a-half seminar. And I really go to show the examples in the mathematics. This is the life cycle cost calculation. I won't go through it. We don't have time. You're not really interested. But in this case, I had a choice of a $78,000 capital investment for sterile filtration or a tunnel pasteurizer at $148,000. And when you do the life cycle cost over 20 years, the pasteurizer would cost us $506,000, and it's a little bit over twice as much as a sterile filter. When I built this brewery in Pennsylvania, I had capital, but it was other people's money. But those other people were partners with myself. It was a $5.5 million brewery. So they didn't get it. Why am I spending all this money when we can get a $78,000 solution? So by showing them the life cycle cost analysis and getting their beer people, so I showed that they didn't understand it, but their CPAs, their chartered accountants said, this is right, the math is right, you're better off in the long run. So here's what that particular machine looked like. That was 5 feet wide and 42 feet long that we installed at my brewery in Pennsylvania. And I'm going to just close up with the last frontier of where I continue to go. And I mean, I'm not making this stuff up. I never really thought about that. But my time with the medical engineering unit, Brian got me to appreciate the fact that you had to have benchmarks. Everything we're doing was trying to improve things. And you had to see where you were and where you're going to. I mean, let's face it, those of us knew Brian, you could, I hope you found his mind, you can almost characterize him as a little boy on a beach. See something shiny. Oh, it's interesting. Why is it shiny? Sees a nice shell. And when you look at his career, Brian has been a little boy on a beach, indulging himself in the things that stimulated him. It was all scholarly work, of course, but his diversity, and maybe that's why he liked having a brewer on staff. He did, and don't take this the wrong way, he did appreciate beer, he did enjoy it, in moderation, in moderation. But I'm closing up with something, this is some work I did a few years ago. I've tried to unify the discussions of sustainability in my industry, coming up with using a technique called data envelopment analysis, which is a way of ranking and scoring in a methodical way. The trouble with breweries is there's a lot of breweries out there who do greenwashing. One thing that brewers always say, I'm a very dynamic and sustainable brewery because I give all my spent grains to farmers. Brewers have always done that, and the reason why we do it, it's cheaper than putting it in the dumpster and dumping it. So cows can eat, whoopee, and too many of us say, oh, I'm sustainable. Brewing is one of the most unsustainable things in many ways. It shouldn't be practiced in a lot of places. We use far more resources. We always have to try to do better, but there are places we shouldn't be. For example, this is a footprint of typical brewery. This is where you're making beer, in this case, 10 hectoliters of beer. A hectoliter is 100 liters. So this is how much energy we're using electrically, thermally, fossilly. But look at the water usage. 5 meters of water are used per meter, cubic meter. So if you're in arid areas, you really shouldn't be making beer. But still, it happens. I mean, we're all working to drive down that number, but there is a limit. You will never get for 1 barrel of water you'll use. And it's funny to talk about reverse osmosis. There's a problem when you're making a food product. If you get wastewater and treat it so you can use back in brewing, we call it the yuck factor. People don't like knowing the fact that you have wastewater that you've retreated. So with that, and yeah, this is the, again, everything's on software. And with these fellows, these are real pioneers. They had to write code. Now you just buy stuff and put in the parameters, make the picture, and let it solve. In this case, it's DEA solver, using this very beautiful technique. It's an elegant technique used for data development and analysis. As a matter of fact, after I gave my first talk on this, there's a professor at the University of Minnesota who actually is implementing it across the engineering school, looking at the different programs, using the same parameters to rank. I'm not quite sure of the full parameters of that, but anyway, that's my email address, and I just want to thank everybody for listening to me. I'd like to thank the Bellhouse family and also Lionel for putting this on. It takes a lot of work to do this. And I think, if I can just indulge everybody for a second, I think if those of us who know and love and respected Brian would say, he would say, oh, you don't have to do this. We're here. And tomorrow at his memorial, you know, it's at the same time that Ireland and Wales are playing in the Six Nations. And I can almost hear Brian would be saying, oh, it's okay. I wouldn't be bothered if you missed it for the rugby. And to be honest, I'd rather be watching the rugby too. But anyway, thank you very much.